Electric field due to linear charge. Hi. In this video, we will find out how to calculate the electric field on a point, due to uniformly distributed linear charge. Let us see an example to get a feel of what we will be calculating. Let's say you are standing in front of a large mirror. Now obviously, all the lights reflecting from this mirror will be reflecting at you. Meaning, right from top to bottom of the mirror, you can see all the lights towards you. This is what exactly happens at any point, when any point is chosen in front of linear charges. Each point of the linear charge will have an effect on this point. Now let's get deeper into this. Let us say we have a rod, with length L, with uniform positive charge distribution. Now there's a term called lambda. Lambda is the total charge on the rod divided by the length of the rod. This lambda is called linear charge density. This we will use in a later part. Now let's say we need to calculate the electric field at a point P, which is at a distance of A. Now in this type of situations, what we do is take a tiny part of the rod, calculate the electric field due to this tiny part. And to find out for the entire rod, we use integration. Now for this tiny part, let's say this has a charge of dq. And has a tiny length of dx. And it is at a distance of x from point P. And because of this tiny length, this has a tiny electric field on dE at a point P. Now, this length dx is so small, that it acts as a point charge. So the formula for electrical field due to point, can easily be applied. Therefore we have dE is equal to k into dq by x squared. Now let's say we choose any random point from rod to point P. And we keep finding dE similarly for all points on the rod. Let's say, the point closest to the point P from the rod is at a distance A. And the point furthest is, therefore, A plus L. So to calculate the entire electric field due to the rod, can be calculated by integrating the dE value. So we have total electric field, or E net is equal to, integration of dE. Which is equal to the integration of k dq by x squared. And this integration needs to be done from point A to A plus L. K being constant, comes out of the equation. Now, remember the term lambda? For this tiny length dx, we have lambda is equal to dq by dx. So we get the value of dq from here, and put it in the formula for dE. Putting the value of dq, we get E net is equal to integration, lambda dx by x squared. On integrating, we get E net is equal to k into lambda into minus 1 by x. When we put the values of A and A plus L, in place of x, we get the final value of E net. So E net is equal to k into lambda into bracket 1 by A minus 1 by A plus L. This is the final formula for the net electrical field at a point P, which is at a distance of A from the rod whose length is L. So this is all about this and how we calculate the electrical field. Let's meet in the next video and find out more about the subjects. Share it with your friends and don't forget to subscribe. If you want to learn more, keep watching the next video.